An emission spectra is a spectrum of frequencies of electromagnetic radiation emitted by a light source. So there are two kinds of emission spectra: continuous, which is your sort of rainbow, it's a full spectra, and line spectra, which are the bright lines that you see that are individual to individual frequencies. So to view spectra produced by various sources, a spectroscope or a spectrometer can be used, which is what you just used there. So continuous spectra comes from a white light source. You can see it through a prism if you put it through a prism, or you can see it through the diffraction glasses that you use. And you see a continuous spectrum of light from red through to violet, and all frequencies are present in the spectrum. And the line spectra, so what we've just been looking at, Mr. Boswell's just about to look at, some sources of light, such as mercury and sodium vapors, do not produce the continuous spectra, but they produce certain lights from certain frequencies. So you see that some of them sort of were like blues and greens, things like that. So these sources, and these are sometimes called discharge tubes, contain low pressure gas, and the gas glows when a high voltage is connected across the tube. The spectrum that is produced is called the line spectrum, and coloured lines spaced out by different amounts. Only specific well-defined frequencies of radiation are emitted. So you get these bright lines, but only at specific frequencies, and each combination of bright lines is specific for specific elements. Okay, okay, get that back. So that was just what we did there, and these are some examples. So hydrogen has bright lines at those specific frequencies, helium at those specific frequencies, and sodium at the other specific frequencies. Okay, and as with the photoelectric effect, so that's the one where one particle of light comes and releases one electron, line emission spectra cannot be explained by the wave theory of light. And in 1913, Niels Bohr, a Danish physicist, devised a theory to explain the production of line emission spectra. You might talk about this briefly in National 5, but this wasn't in sort of the National 5 curriculum, but it is in the higher curriculum. So you might have talked about Bohr's atom and how he realized that the electrons were positioned in atoms. Okay, so basically we know that electrons are around the outside of a nucleus. Okay, and if you're a chemist, you probably know a little bit more about the different energy levels and things like that. Okay, so you know that there are different energy levels can contain different amounts of electrons. You don't need to know it in that much detail here, but you do need to know, in the important part in physics, is each energy level is a different type of energy, okay, a different amount of energy. Okay, so each energy level has a specific energy associated with it. Okay, and it takes that amount of energy for an electron to jump up to a next energy level or to drop down to the energy level below. Okay, and these are very specific, very discrete energies. Okay, so instead of just the electrons just being anywhere around the outside, they are in these states, these energy states. And this one's the one sort of nearest the nucleus, and then as you go out, there's another one, and another one. You can see the gaps are getting smaller and smaller as you go further out. The energy gaps, the difference in energy between them, smaller and smaller. Okay. So Bohr used the ideas of Einstein and Planck to update Rutherford's model of the atom. That was just the electrons orbiting. Bohr suggested that the electrons in a free atom occupy discrete or quantized energy levels. So a free atom is one in which is not affected by its neighbouring atoms. So those are the energy levels there. And the lowest energy level of a system is called its ground state, and that's the one nearest the nucleus. Okay. And there are a limited number of allowed energy levels, so electrons can't exist in between these energy levels. They're either in an energy level or a different energy level. And higher energy levels are called excited states. So ideally, the electrons would prefer to be in the ground state, but they can get excited to higher states as well. The energies of electrons in the various orbits are, by convention, given negative values, which is really annoying. So when an electron moves to a higher energy level, it gains energy and moves to a less negative energy level. Okay, so that's the complicated part here. And energy is needed to free an electron from its atom. An electron just freed from an atom has reached zero potential energy value. When the electron has escaped from the atom, ionization has occurred. We know that ionization is the creation of a charged atom. So in other words, the ionization level is reached when the electron gains enough energy to leave the atom completely. Okay, so basically there are steps for the electrons to go up. Okay, and potentially they could leave the atom completely. They don't tend to, they tend to just move up and down energy levels. Okay, so electron transition, this is the important thing about the spectrum. So electrons can move between energy levels by either absorbing or emitting a photon of electromagnetic radiation, usually light, with just the correct energy to match the gap in between the energy levels. And as a result, only certain frequencies of light are emitted, as there are a limited number of possible energy jumps or transitions in each element. Okay, so each atom of each element has these specific frequencies of these specific energies of the energy levels. So there are two things that can happen. You can have an electron that moves up to a higher energy level, a more excited state, with more energy. But for it to do that, because we know that electrons prefer to stay as low energy as they can, for them to get the energy to jump up, they absorb a photon. They absorb a photon, a little packet of light, and then they have enough energy to jump up to the next level. Alternatively, when they're in this excited state and they don't want to be anymore, they want to go back down to the less excited state, the electron will move down, but it will give out a photon. Okay? And that photon, the energy of that photon has to be equal to that energy difference between the two energy levels. Okay? So in the top one, for the electron to move upwards, it needs to absorb a photon of energy, if we call this one E1 and E0, the energy will be E1 minus E0. So it needs that photon to be exactly the energy difference between those two states. And when it goes down the way, it will release a photon. But that photon will be exactly the energy between the two states. So it's all about the energy differences of the energy levels. Okay. So for it to go up, for it to go up an energy level, it has to have some energy to help it do that. So it takes that from a photon. And if to go down an energy level, it's got too much energy, it needs to give it out, and it gives it out in terms of a photon. And these two things correspond to the different spectra. So when they absorb a photon, that's where you get the line absorption spectra. So you get the black lines along this continuous spectra. So the black lines along a continuous spectra, they're the photons that have been absorbed. Whereas this one, the photons being emitted, when the electrons drop back down again, that's your line emission spectrum. So that's those lines correspond to those photons being spat back out because they don't need that energy anymore. Okay, so that's where the spectra come from. That's the physics behind the spectra. So we're not actually going to start the sums involved in this, but that's the physics behind it. So it's all about the difference in energy levels. Okay, we'll talk about working that out next lesson because we don't really have the time to go into it in that much depth. So what I'm going to do is I'm going to skip past 18 and 19 because those are the ones that we're actually going to look at. And we're just going to look briefly at more about Spectra because again, we've done this in National 5. And what's quite good is at the bottom of that page, you've got the examples, and I've got it put in colour, of absorption and emission spectra. So your absorption is absorbing photons, so taking those photons out of the equation basically, for it to jump up the way, for it to gain extra energy, and you've got black lines instead. Whereas the emission one is when it falls back down again and it gives out a photon of light at those specific frequencies. So those bands of light are corresponding to the photons that it's been given out. Okay. So just a few more bits more about spectra. I'll let you read most of this yourself in a second. But line emission spectra are emitted from low pressure gases where the atoms are free. Continuous emission spectra, which is rainbow, seen from solid, liquids and high pressure gases. In sources like filament lamps, the atoms are not free and electrons may be shared in bonding with other atoms. This results in an infinite number of possible transitions and an infinite number of lines. Okay. So I'll let you have a read through the next few pages. Just a reminder as well, National 5, Fraunhofer lines. They are an absorption spectra that comes from the sun. So if you did look at the sun, which you're not going to look at the sun directly, through a spectroscope, then you should see lots and lots and lots of very thin black lines across a continuous spectra. Okay, and that's how Fraunhofer, they're called Fraunhofer lines, and that's how you can work out what kind of elements were around in the sun. Okay, so what I'd like you to do is just read through those, that's pages 20 and 21, and then you can continue with your questions, but we don't really have that much time left. And then tomorrow we'll talk about working out, putting numbers to spectra. Okay, so read through page 20 and 21, and just continue with questions.